Learning objectives. At the end of this topic, you will be able to understand the concept of similar figure, describe similarity of triangles, solve problems involving similarity of triangles. Introduction. Let's begin this chapter with a quick recap of what we have learned about triangles in the previous classes. We have learned that two figures are said to be congruent if they have the same shape and the same size. All circles with the same radii are congruent. All squares with the same side lengths are congruent. And all equilateral triangles with the same side lengths are congruent. Two figures having the same shapes and not necessarily the same size are called similar figures. In this chapter, we shall study about those figures which have the same shape but not necessarily the same size. In particular, we shall discuss the similarity of triangles and apply this knowledge in giving a simple proof of Pythagoras' theorem learnt earlier. Similar figures. Let's view some images from nature. What do you observe? Now, let's move to some geometric shapes. In image 2, we can observe that two circles do not have the same radius. They are not congruent to each other. We can note that some are congruent and some are not, but all of them have the same shape. So they all are what we call similar. Note, two similar figures have the same shape, but not necessarily the same size. Therefore, all circles are similar. As observed in the case of circles, here also all quadrilaterals are similar and all equilateral triangles are similar. From the above, we can say that all congruent figures are similar, but similar figures need not be congruent. Let's perform a small activity. Here you can view photographs of different sizes of Lisa. Would you say that the three photographs are similar? Lisa's photographs relate to stamp size, passport size, and postcard size. She generally takes a photograph on a small size film, say of 35 mm size, and then enlarges it into a bigger size, say 45 mm or 55 mm. Thus, if we consider any line segment in the smaller photograph, figure, its corresponding line segment in the bigger photograph, figure, will be this, really means that every line segment of the smaller photograph is enlarged, increased in the ratio 35:45 or 35:55. If we consider inclinations or angles between any pair of corresponding line segments in the two photographs of different sizes, we shall see that these inclinations or angles are always equal. This is the essence of the similarity of two figures and in particular of two polygons. We say that two polygons of the same number of sides are similar if 1. Their corresponding angles are equal and 2. Their corresponding sides are in the same ratio or proportion. Note, the same ratio of the corresponding sides is referred to as the scale factor or the representative fraction for the polygons. Example, world maps, that is global maps, and blueprints for the construction of a building are prepared using a suitable scale factor and observing certain conventions. Let's cite a property of polygons. Two polygons of the same number of sides are similar if all the corresponding angles are equal and all the corresponding sides are in the same ratio or proportion. In the figure, we can observe that quadrilaterals ABCD and PQRS are similar. Note, if one polygon is similar to another polygon and the second polygon is similar to the third polygon, then the first polygon is similar to the third polygon. In the two quadrilaterals, a square and a rectangle of figure, corresponding angles are equal, but the corresponding sides are not in the same ratio. Hence, two quadrilaterals are not similar. In the two quadrilaterals, a square and a rhombus in the figure, corresponding sides are in the same ratio, but their corresponding angles are not equal. Again, the two polygons quadrilaterals are not similar. Thus, either of the above two conditions 1 and 2 of similarity of two polygons is not sufficient for them to be similar. we know that triangle is also a polygon. Hence, we can state the same conditions for the similarity of the two triangles. 1. Their corresponding angles are equal. 2. Their corresponding sides are in the same ratio or proportion. If corresponding angles of two triangles are equal, then they are known as equiangular triangles. A famous Greek mathematician, Thales, gave an important truth relating to two equilateral triangles as shown. The ratio of any two corresponding sides in two equilateral triangles is always the same. It is believed that he has used a result called the basic proportionality theorem, now known as the Thales theorem. Click on the basic proportionality theorem to know more. Draw any angle XAY and on its one arm AX, mark points, say 5 points, P, Q, D, R and B, such that AP is equal to PQ is equal to QD is equal to DR is equal to RB. Now through B, draw any line intersecting arm AY at C. Also, through the point D, draw a line parallel to BC to intersect AC at E. We can observe from constructions that AD by DB is equal to 3 by 2. Measure AE and EC. We observe that AE by EC is equal to 3 by 2. Thus, we can say that in triangle ABC, DE parallel to BC and AD by DB is equal to AE by EC. This is due to basic proportionality theorem. Statement: a line parallel to one side of a triangle divides the other two sides into parts of equal proportion. Given. In triangle ABC, a line drawn parallel to BC cuts AB and AC at P and Q, respectively. To prove, AP by PB is equal to AQ by QC. Let the point P divide AB in the ratio of 1:m, where 1 and m are natural numbers. Let the point P divide AB in the ratio of L:m, where L and m are natural numbers. Divide AP into L and PB into m equal parts. Through each of these points on AB, draw lines parallel to BC and to cut AC. Draw lines parallel to BC to cut AC. Proof. Step 1. Cut AP into equal parts and draw lines through these points parallel to BC. Step 2. By intercept theorem, AQ is cut into equal parts. Step 3. By step 1, QC is cut into m equal parts. Step 4. By construction, AP by PB is equal to L by m. Step 5. By step 2 and step 3, AQ by QC is equal to L by m. Step 6. By step 4 and 5, AP by PB is equal to AQ by QC, hence the proof. Theorem. If a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side. This theorem can be proved by taking a line DE such that AD by DB is equal to AE by EC and assuming that DE is not parallel to BC, see figure. If DE is not parallel to BC, draw a line DE dash parallel to BC. So, AD by DB is equal to A dash by E dash C. Therefore, AE by EC is equal to AE dash by E dash C. Let's take some examples to illustrate the use of the above theorems. In the given figure, PQ is parallel to MN. If KP by PM is equal to 4 by 13 and KN is equal to 20.4 centimeters, find KQ. Let's take some examples to illustrate the use of the above theorems. In the figure, if LM is parallel to CB and LN is parallel to CD, prove that AM by AB is equal to AN by AD. Summary. Let's summarize the topic. Two figures having the same shape but not necessarily the same size are called similar figures. All the congruent figures are similar, but the converse is not true. Two polygons of the same number of sides are similar if 1. Their corresponding angles are equal, and 2. Their corresponding sides are in the same ratio, that is proportion. If a line is drawn parallel to one side of a triangle to intersect the other two sides in distinct points, then the other two sides are divided in the same ratio. If a line divides any two sides of a triangle in the same ratio, then the line is parallel to the third side.